I thought it might be good to make a couple of videos on sort of the hard mathematical part of neural networks that might be too boring or not super productive to do in class, but which we should probably go over somewhere. Um, so here's a picture of a neural network. This is one layer. So consider this middle thing is layer L, and before layer L comes layer 1. And after layer L comes layer L plus 1. And so each layer, thinking of all of these as being, well, layer L is like a hidden layer anyway. So over here somewhere is the input layer, over there somewhere is the output layer. So there are these bias nodes up top that have outputs but no inputs. Um, each node has some kind of activation function, which we're calling theta. So for example, theta could be hyperbolic tangent, or it could be ReLU or ALU, or some other activation function. So I'm going to be considering what happens when you go from node I and layer L minus 1 to node J and in layer L. And so yeah, so this video is going to be just on how to train neural networks, but um, before you understand how to train them, you kind of have to understand how information flows through from layer to layer. And so we need some pretty complex note. We need triple subscripted notation because there are a lot of wires here. So you have these indexes I and J that count along nodes. You have these indexes L, which count layers, and often you have to combine them all together. So for example, Wijl right here is the weight from this is basically this is the output of node I and layer L minus 1 to node J and layer L. So hopefully you're familiar with this from class. So the output of node I and in layer L minus 1 is called xi. The vector of all of them for every single output we just call x bar. So x bar L is like the sorry, L minus 1 is the vector of outputs of all of these. But when we put a subscript, we're just talking about a particular one. So this is subscript I here. So we're just talking about the output from node I. And so, you know, all of these wires have a certain weight. In fact, they're weighted by these things. And this thing that we call WL is just the matrix whose elements, whose Xij entry is Wij. Okay, so that's what WL is. So now when we arrive at a particular node here in layer L, all of the weighted inputs get summed. So what gets summed here is the output from each of the previous nodes multiplied by its weight, and then you add those up, and that's what SJL is. So SJL is the input to node J in layer L. So now this, you know, this process sort of recursively continues from layer to layer. So node J will have its own output, and then Finnegan will begin again, and the whole thing will happen in the subsequent layers. Okay, until you get to the very end. We call the very last layer layer L. And so this is the output of layer L will be this thing, which is some activation function applied to the input to the last node. You're thinking like at the end of this process, there's some last node over here in layer L. And so this has some input, which is SL, and then it has some activation function, which you apply, and then this is the final output of the neural network. So that's the hypothesis that it eventually produces. So often for this last node, let's say that you've been using hyperbolic tangent um, for an activation function. Often in the last node, you just leave it off and make this kind of a special case where the transition function is just the identity function. So you definitely do that if you're doing regression, because then the output is just sort of a dot product of some vector in, Euclidean space with some weights, which can produce any real number as an output. And so that's what you want in the case of regression. But often people still do it in the case of classification. And the reason is that you can get sort of without doing that, if you just threshold this SL like this, then if you have if SL is a big number, it gets thresholded up here to something near 1. And then when you look at the gradient there, the gradient is approximately 0. And similarly, if SL is a big negative number, then this gradient over here in this part of the sigmoid function is also approximately 0. And it makes information move backward through the network during the training process very slowly, because it gets multiplied by something that's approximately 0. And so it takes a long training period for the effect of all these small numbers to percolate backwards and affect the weights and the lower layers during the training process. So one way to stop that is for the last node to use something that is not sigmoidal, and then you get gradients that are just sort of they're not near 0. So that might give you kind of a head start in pushing back through the network during the training process, and bigger numbers that can help the weights in the lower levels change a little bit faster and make training go faster. Okay. So great. So this is the output of the last layer. This is the error that accrues from the difference between the network's prediction on a single input and the output. So this is the label. This is the known value. And here we're using mean squared error. And so this is the pointwise error that's caused by a single labeled training pair, x, y. So you'll have some hypothesis produced by the network. That's what that is. You'll have some true value, and then the square of their difference is the error. So a big player in this explanation later on is going to be the partial derivative of E with respect to SL. And I just want you to be ready when, oh, sorry, this should be capital L here. So that's, computing what that is just a calculus 1 problem. So if, you have to know what theta prime is, whether theta is like ReLU or hyperbolic tangent. So that's not a problem. And then even though it is a little bit tricky for people whose calculus is not strong, it should be fairly easy to figure out what that is. Okay. So this part of the process where you produce the eventual hypothesis is called forward propagation. So that starts all the way back at the input layer. So the input layer, the inputs are just the bias and then the d-dimensional inputs. And then to go from a previous layer to a subsequent layer in the forward direction, you use the forward propagation algorithm. So when you go forward, these are the outputs of layer L. So that's like these things over here, the outputs of layer L. To get those, you stack an H, you stack a 1. That 1 is for the bias node here in layer L. And then this is vector notation for applying the activation function to all of the inputs to each node respectively. So for every single node here, you have S bar JL. And then if you apply theta to that, so that gives you a vector, which is called S bar L. And then if you apply theta to every respective entry of that, that's what this notation is saying. And you can recursively get S too. So if you have the outputs for the previous layer, you multiply them by the weight matrix, which is this thing. You have to take the transpose to make it work outright algebraically. But that's basically it. So that will produce all of these little xj's here, and so that will give you SL. All right, and so the training is the difficult part, I guess. Forward propagation is pretty easy. So to train a neural network, you want to do gradient. Well, so the most popular algorithm is backpropagation, which is based on gradient descent. And so the idea of gradient descent in general is that you have some weight vector, and you repeatedly alter this weight vector by subtracting some small constant called the learning rate, which we'll call eta, times the gradient of the error. So we call our end sample error over the entire data set En. So you have this formula. And stochastic gradient descent, this is replaced by the gradient of the pointwise error. And so even this, you can compute this. So this big cumbersome thing, if you do want to do batch gradient descent, this is just the average of all the pointwise gradients anyway. So either way, you can get everything just from knowing the gradient of the pointwise error, which is good because this is simple. Okay, so we want to make this complicated process a little bit more simple. Okay, so the idea of backpropagation is to compute this guy, which is the gradient of the pointwise error function. And the gradient is over every weight. So what we're calling W bar here is every single weight in the entire network. And so we've been representing that as like just the list of all the weight transition matrices. Blah, 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 out to WL, okay? All right, so that's like, possibly thousands of parameters. So if you want to take the gradient of E with respect to W, one way of representing that is just the list of matrix partial derivatives. So it's the partial derivative of E with respect to the first weight transition matrix, and then the partial derivative of E with respect to the second weight transition matrix, et cetera, et cetera, et cetera. So this contains all the same information as the gradient here. Namely, it's the partial derivative of E with respect to every single weight variable. It's just that for convenience, you're representing them, sort of geometrically arranged in matrix form. But that just makes things more simple, so it's good. So this is basically the gradient here. So now we've simplified the problem again to finding this character, which is the partial derivative of the pointwise error with respect to just one of the transition matrices. So let's call this one L. And so the key formula for doing that is this equation here. And we actually are going to prove this equation using calculus in a second, maybe in a second video. So what this delta bar thing is called the sensitivity vector, and what it means is it's how sensitive the error is to the outputs of layer L. So this is the definition, and this thing can be computed in terms of so XL and delta L. So this means that we can do gradient descent and train the network if we only have an algorithm for computing these deltas. And so those deltas can be computed recursively. So there's a base case, which is the last layer. And so in the last layer, we talked about this before. This is basically a calculus 1 problem. You just have to, use whatever you have to know the derivative of theta, whatever theta is, and you have to be able to use the chain rule. But otherwise, it's totally simple, because what you're taking the derivative with respect to here sort of actually is the variable. So it's just a calculus 1 problem. And then there's this other key equation here, which gives you the sort of recursion step. So suppose that delta L plus 1 is known, then how do you compute delta L? And it turns out that this is how. And so in a second video, we're gonna do the derivation that proves that this is the formula. But let me say a couple more things here. So this, of course, is a vector quantity, because S bar is a vector. So these will be the vector of all of these derivatives with each entry respectively. This times here means this is like NumPy broadcast multiplication. So it's just element by element multiplication. So you'll have some vector here and some vector there, and then you element-wise multiply them. This obviously is just a matrix product, and so we will explain where it comes from in a second. This notation on the side here means that you ignore the top entry in this vector. So if you figure out the dimensions of this multiplication here, what you'll discover is that this has one dimension too many. And that's basically because the SLs, so the SL is coming in here, and there's one of those for every one of these nodes. But when you apply WL plus 1 to delta L plus 1, you get you get a vector that has this length. So there's one entry at the top that corresponds to the bias node, but it just turns out not to be relevant to the process, so you just ignore that. And then you do element-wise multiplication across here, like this. And that computes the sensitivity vector for the previous layer. All right, and now if you can compute those deltas, then you can beat the game, because we have this equation here that basically computes the gradient, and so now you can do gradient descent or batch gradient descent or some other variation of gradient descent. So I want to show you a worked example. So let me go to the top here. So these outputs, I did it kind of by hand, and I also used a program that I validated by checking the outputs on a worked example from our textbook, Learning from Data. And so also by running the code on real data, I'm fairly confident that this works, so this should all be correct. So you have this neural network right here, and the inputs to it are 1 and 2. So here's 1 is just the bias input, and then 2 is going to go in here. And we're going to do forward propagation and backward propagation. So for backward propagation, we're going to assume y is 1. So this is just doing the computations that we just outlined. So you can sort of pause this and compute these as you will. I made a mistake when I was scanning this. So here's the end of the forward propagation process. You get all the S's and all the X's. And now the backward propagation part begins. We're going to assume that y is 1. So this is that calculus 1 problem that I alluded to earlier. So if you're using hyperbolic tangent, like in this problem, then theta prime is just 1 minus theta squared. And one nice thing when you're using hyperbolic tangent is that you don't need the S's. But when you write your code, you should probably still write things in terms of the S because it makes it easier to change activation functions. You know, you want to be able to sort of easily switch out activation functions. So just write things in terms of theta and theta prime of S, I think is the best way. Because then you can change your activation function with one line. Okay, so computing all these values, blah, blah, blah. I accidentally scanned that page twice, so this is exactly the same. And now here's the last part of the derivation. So finally we get down to delta 1. And notice that these that delta has gotten, this coordinate anyway of delta has gotten very small. And by the time you get down to the derivative of E with respect to the first transition matrix, these values, which will be used in gradient descent to update those weights, are pretty insignificant. So this is a sort of a general problem called the vanishing gradient problem. And the problem happens because the deltas get too small. The deltas get too small because theta prime is too close to 0, and theta prime is too close to 0 because S is too extreme, either in a positive or negative direction. And so with the deeper the network, the more layers, the worse the vanishing gradient problem becomes. And with deep neural networks, since 2012, there's been a lot of progress on ways to prevent this problem, like using the ReLU activation function, and also some different strategies for initializing the weights of the network. I'm going to stop this video, and I'll do another one with the calculus.